key point. After we presented the abstract, we got recently permission to show data about the effect due to high current density using artificial intelligence. So this one before was not you can find in the abstract. So I would like to speak a little bit even about this point, if I have time. I have several transparency, but I use just for line guide. And we realized shortly from the beginning of cold fusion era that the effects happen only in non-equilibrium condition. It has to be very strong and very fast. This was our key point to go over. We have done comparison of the effect of large current with artificial intelligence. We before know 3-4 effects due to high current, but artificial intelligence is more intelligent than me, and they found in total 13 effects, even related to hydrogen and deuterium absorption. So we speak a little bit. Our system was thinked optimistically, so we use electronics as simple as possible and cheap as possible for practical application. So we use commercial device with very little changing, because our hope is to go to practical application. We started this work from March 89. So key point, non-equilibrium, equilibrium should be very fast and very strong. You can give any kind of non-equilibrium, electric, magnetic, mechanical, acoustic, nuclear, but we concentrate on the electric because it's very easy to make. Just is the reason. Now electronics is very powerful, faster as time, so match our need. Moreover, before in the beginning, we think that we will have a very high purity material, ultra-pure palladium, 99.9995, we get a real optimal result. But we found 0. It means with ultra-pure material, nothing happens. So need some impurity or some dislocation or something strange. Okay. The benchmark of cold fusion was the experiment of Fralick in 1989. In December, he demonstrated that the cold fusion is real, but the data was kept confidential for over 20 years. So only few people know about. And it was, I think, 20 years of delay, but it's just my opinion. After the experiment, the fracture would be known, everybody, they realized the effect is real. So we were looking material has to be low cost, and we found Constantan match this need. And moreover, with the Constantan, possible to use hydrogen apart deuterium, so always reducing cost. In almost similar time, group of Tagashi, Vamura, Kasagi, Klimprat, everybody developed independently from me. They don't know about me. Alloy, copper, nickel. So completely different. But the conclusion was the same. And another point, recently, Professor Alexandrov, Dimitar, showed data where there is a very high temperature using an approach different from my original. He warm a Constantan wire, 1050 micron, at a very large temperature, 960 under vacuum. When it's clean, he close the chamber and put abruptly deuterium 0.1 bar, and the reaction was extremely fast and violent, maybe temperature over 1,500, 2,000, I don't know, really giant. And this, I have idea to use this strange phenomena discovered from Demeter for space application, and I give immediately such information to people involved in the space transport. But up to now, I don't know what happened. Okay, about copper nickel, the first people that think that was good material with deuterium was Brian Hearn in 1995, but maybe nobody know about it. It's written in a patent, but really nobody know. Sorry. Okay. The model we think are match our data is the flux model developed from Fukai and Sacker. And this model is not in disagreement with the model of Preparata. So we want to use two effects, longitudinal excitation and transversal. Longitudinal was our habit from 1993, very, very old time, so we have not enough experience. Transversal, you used a way to excitate the surface. So it's governed by Pascal law or electric barrier discharge. Other point is we have seen sometimes very high temperature melting away the material. We think it's dangerous because destroy. So we want now, we are working to have a hybrid system. The bulk is tungsten, so 3,400 Celsius, and over several layers of copper, nickel, low oxidation, so on. So we hope it can be a way to reduce the problem of self-destruction of the material, but just is our hope. It's our reactor, quite simple. It's a constant wire inside a glass tube coiled. Put the reactor. The geometry is coaxial geometry, but the main difference in usual coaxial cable, the active is the center, and outside is the copper insulation. In our case, it's reversed. The latest changing, but 1 year before, was to substitute the counter electrode that before was just a thin iron tube with a coil of iron constantan 2. For several reasons, maybe long to explain, but it was one progress. Set up our very simple instrumentation. The tube is about 40 centimeters long, glass, and there is some network of protection because sometimes we have explosion, and to protect from debris of glass, we make net. The effects we use are several. Most are older than 100 years. The first one is thermoionic emission due to low working function materials. It was used in the old vacuum tube. So it's a mixing of calcium, strontium, barium, very, very old technology. The second one is the Pascal law when we want to excite the surface. The third one is electric barrier discharge, is more kind way to excitate the surface. And as are more modern, electromigration from Sorko and collaborators in 1930. They do that. So in the electromigration, the quality factor is volts over centimeter of the wire. the deuterium coherence developed from preparata is a jump because we consider all the wire where the coherence is made. This is extremely nice effect, but more difficult to get. So we see few times exciting, but extremely low reproducibility. And about the place where happen the reaction, we think the superloading model from Fukai Stacker can be good. Here is shown the usual, with pointer, okay, the usual curve of low working fashion materials. We are working in this region, barium, calcium, strontium. And moreover, because the surface is sponge, the effective area is 100 times larger. This is maybe well known to some people, curve of Pasken, that show how the discharge voltage changing the distance between anode, cathode, and the type of gas. So now we are working usually with hydrogen and argon, or deuterium and argon, and calibration helium-argon. So changing the pressure, we can go from a region where this point don't happen because we have a limit on 1000 voltage, or enter this other. When we are able to enter in this region, there is an extra gain of energy. The weak point, the energy local is very high, so it's easy to destroy the material. So we make some improvements to avoid this side effect. Here's the usual DBT phenomena discovered from Siemens in 1857, so more than 200 years before. In now a short summary about the artificial intelligence. Our wire is at 200 micron, cross area 0.034 millimeter, and typically we give a current density, current between 5 and 10 ampere. So in the case of a 10 ampere, neglecting skin effect, we have about 380 ampere per square millimeter. So the artificial intelligence replay. We have electromagnetic effects, electron cloud dynamics, Joule heating, thermal expansion and lattice strain, so electromigration, magnetostriction, electron cloud, so really a lot of phenomena just due to large current in pulsed condition. We know some of this effect, we guess some, but never we have so detailed replay. It is the quality factor. What happened? Changing the current density. So we can enter maybe 11 of 13 possible effects, but we can go to higher current density with some improvements. So maybe 9 effects, the rank up to 9, where is interplay of active material preparation and anomalous heat. I give to you all these documents so you can read them with more time. The schematic of the circuit, I go immediately. This is a comparison of wave using AC current, unipolar AC current. By dimmer, the dimmer is a phase changing of the power given to the wire. How long I have? Excuse me. How long time? 5 minutes. Okay, this is our typical effect when we use unipolar negative pulse. So the point is moving from here 2 years, we have increasing about a factor 4 about the peak voltage. The peak voltage is useful both for electromigration phenomena and for high current density. So we working with these methods. The general setup of the system looks complicated, but the main aim was to reduce the energy waste to activate, to give the energy. So just very, very basic electronics. This is a new point, is the system that we developed to give the high voltage to the counter electrode. It's based on a fast transformer up and the system to limit the maximum voltage that we give to the counter electrode and the maximum current that we can give using constant current diode. The point is, this is not feedback system, otherwise you will get oscillation because there are several capacitive stray and with inductance easy to get oscillation. So it's no feedback, and this happens only when the system decides it's necessary to happen. Primitive, simple, and reliable. Now I show you data. The first one is a typical pulse. At low power now is 71 watt. The pulse has a peak current in this experiment about 6 ampere and voltage about 200. Repetition 50 Hertz, so 20 milliseconds. Here is detail about the phase of current voltage. There is no delay. It means the data are reliable. And the green is the power applied. So the peak power in this region, peak, is about 1 kilowatt and 200 watt, so about 20 times larger than mean power. So again, in the line, strong power for short time. He has shown the Pascal regime when we increase the pressure, so no discharge apart beginning. And when you are working with the proper pressure, a lot of high voltage discharge up to 1100 volts. So in some way, this is under control system. This experiment was done using S calibration. We suppose that in this condition, there is no HSIT. So data are conservative. And we calibrated in this condition, and changing the total power, we have, for example, at 60 watt, 14 watts due to longitudinal excitation, and 16 watt in total using both. But we have to consider with transversal excitation, we have 2-3 watts lost because of the transformer and so on. So the true gain scientific is larger. At 80 watt, we have input, we have totally about 22, 23 extra power. This experiment was done reducing the pressure to check what happened, and the data are qualitatively similar, in some cases even better. Further consideration, the Paskin, we were forced to move from the old laboratory to new one because according to my institute, I am too much old to make experimental activity. I can just use computer. For me, it's not good for me. So
One more minute.
1 minute? Okay, so I have to move another place where I can play with a real reactor. And the experiment was locked for 2 weeks. When we start again, really damaged. So it means that Fugai model is correct, can be correct because the system is metastable. So if you don't give power, the metastable region disappears. The Pascal regime happens only when the temperature is larger than 650. It means the low working material is necessary. And we are planning to use a hybrid system with a tungsten wire, properly coated. So we hope to have larger high power because the surface excitation is more energy considering better than the bulk. So we want to go to some practical, but I don't know if we will be able to make. And finally, we think deeply European Union about the project, and Conrad and Maurizio Maggiore were really useful. We work from 13 years with a North Test company that cross-check our most critical data, but they don't want to be in public. Carpage, Anthropocene Institute, Franklin and other helped me from very long time, so I think. It's another big, small company in Italy that gives some support. I finish.
Thank you very much, Professor Celani. We have time for one or two questions.
Okay. There is.
I think that your research is very important, so I need to confirm that. Why do you use select a constant?
Sorry? Okay, the history is very, very complicated. I didn't know about the Aren paper, and I suppose, just was a guess, that one old experiment from some people, they confuse the result, and we think that the real origin was the thermocouple J-type, that it was iron Constantan. So we want to test, so it just was a coincidence, nothing more.
I see. As my understanding, the cold fusion occurs at the grain boundaries. So I think that Iwamura's...
But not only, there are 2 points. Bulk effect, always is more reproducible, more easy in some way. You have to prepare the material, but once prepared, it works very. Our last experiment is working from over 10 months. Even it was locked for 2 weeks because transportation. So strong. It's only 200 micron, length 2 meters. So people say, oh, after going the wire destroyed. Not true. To be careful, you have to, but no so critics.
Yeah, I'd like to confirm the cause of a good property of constantan. I Googled that. The constantan grain boundary grain is uniform, more uniform than others. And because that the constantan has the nickel
kappa.
Yeah, nickel kappa, that both is FCC. So yes. The property is better for the cold fusion.
Okay, but here's one point. If you use a virgin Constantan as cell from the company without surface treatment, you have to wait very, very long time. So not efficient. So we prepare the surface using oxidation and painting low material and adding iron. So there is okay, I don't know.
So we need to confirm that the constantan available commercially is not good so for the cold fusion, right?
No, it's good, but you have to work. But with palladium, you work after 1 month, 2 months, always works, little but always. With Constantan, if you don't prepare before, you get nothing. So you have to modify. modify surface to have a sponge surface, so extra work. But the cost is 100 times less than palladium. And it works with light hydrogen. So both is a strong argument for a practical application. So we are going to, anyway, we make test with the deuterium. And with deuterium, when it works, it's a little bit better than hydrogen, but the cost is higher. So it's compromise, everything, like the life.
Thank
Okay,
you.
we have to move on to the next speaker. Thank you very much, Professor Celani.